My name's Luke Barron, no habla español. I understood about 5 words my wife had said during hers, such as tal vez, zapatos. That was about it. So I think I understood this assignment a little bit different than she did. I was told to talk about what I do for work and what my work does. So I won't go quite as deep into my backstory and how I became an engineer, but I will start with a little bit. I decided to become a mechanical engineer. Well, at least I knew I was going to become an engineer in grade 2. So my sister is 10 years older than me, and she became an engineer after her 12th grade when she went to university. And that's when I decided I'm really good at math, I like science, I'm gonna go do this also. And then as I was in high school, I really liked cars, so I said, I'm gonna become a mechanical engineer. And that's basically how I chose to do that. And I think it's really important that we do have engineers in both science, technology, math, all of that, because we need to keep progressing the world forward. It's you girls, and we all know, and it's been proven that girls are smarter than guys, so it's up to you, not us, to really drive the world forward. And when you see something that's different or you question why, that's what really drives innovation, I feel. So when you don't like something, go out and be that change that changes it. Go out and make that new thing that works. Discover that new thing that helps humankind in itself. So one of the things I actually wanted to go over really quick, because I think innovation and invention is really cool, was when Louisa was talking about her first job out of college, working for Micromotion and their Coriolis flow meters. She actually didn't even mention how that got started. So there was an inventor in Boulder, Colorado, and he noticed one day while playing with his girls in their yard, he was playing jump rope with a watering hose. So he was swinging it around like this. So you had this motion of it going back and forth. And when he turned on the water to the hose, it made it wiggle like that. And he questioned why that happened. So he thought it was funny because it would trip up his daughters that were playing jump rope with their hose. And what it was the inertia. So you have the mass of the hose going back and forth, and then all of a sudden you have the mass of water going in a different direction. And that caused the hose to kind of twist on it. So imagine if you were running in a straight line and your friend pushed you from the side, you're not going to go directly to the side. You'll kind of go off at an angle because you have that inertia of you moving and then the inertia of you going to the side, which makes that angular motion. So that's actually how that flow meter that she was talking about where she worked got invented, was just by an observation of somebody saying, why is this happening? So I think that's really, really important as you go through life to question those things in the world of why are these things happening that you see that you don't know the answer to. So I work for Maxar. We are a satellite company based out of Colorado and California. And essentially we take photographs from space. So when you look at Google Maps, all those images from satellite views were taken with our satellites. So we capture about 3.8 million square kilometers of imagery every single day. So we have 4 satellites that orbit above us, and we're constantly taking pictures with them. We design and manufacture the spacecraft and components And we essentially tried to map the whole world itself. Our archive of imagery that we've collected is over 125 petabytes. So 1 petabyte is 1,000 terabytes. 1,000 terabytes is 1 gigabyte, just to put that into perspective of how much information we have collected. So within Maxar, I work for this program called the Direct Access Program. And essentially we provide the government, defense, and commercial customers access to use our satellites to capture their own imagery. So it's not just Maxar that's always taking pictures. We're essentially renting our satellites out to customers to go collect their own imagery. And sorry if this graphic is kind of hard to see. So you have a customer ground terminal in the lower left. That's essentially just an antenna. So like you'd see a satellite dish and some hardware computer components. They can then talk directly to our satellite. So our satellite will fly overhead. That antenna will point itself at it. They'll communicate with it, tell it what pictures to take, and then get those pictures streamed right back to that antenna system to be able to view them almost immediately. So within that, these are called DAFs, so DAF, so a direct access facility. So it's a ground terminal that allows communication directly to our satellites. Within there, there's a suite of software for customers to manage what orders they want to take. So they'll have a map in there, and then they'll draw little boxes or circles or whatever shapes they want of areas that they want to collect. So if I wanted to collect a picture here over your school, I could just draw a little box over Medellin, have the satellite fly over, take that picture, and go get it. Then after we decide where we want to take a picture, we have to plan out how to take that picture. So people rent our satellites for minutes at a time. So the minimum amount that we allow them to rent is 2 minutes at a time. So usually a customer will rent it for 2 minutes, and they'll try to take as many photographs in that time as possible. So that's called collection planning. So it's how they actually plan out how that satellite's gonna move and take pictures. And they're trying to plan around the weather, most of all, because it makes for a not good picture if there's a bunch of clouds in the sky. So usually they'll have orders spread out, and the ones that we predict aren't gonna be cloudy, because they'll look at a weather forecast, they'll go in and take pictures of. After that, they'll use an antenna system similar to that satellite dish right there to talk directly to our satellites and downlink from them. And then after that, that hardware stack that you see on the right, it'll then take that raw data that it downlinked from our satellites and produce it into a picture itself. So all of our satellites right now have what's called a sun synchronous orbit, which means they travel from the North Pole to the South Pole and then back around again. And this gives us predictable shadows when we take a picture because it crosses the Earth at around the same time every single day. So we have 4 different satellites. 3 of them cross at approximately 10:30 a.m. every single day. So that way the shadows, when they take a picture, it's very predictable from day to day, so you don't get a big contrast between pictures. And another one that we have, which is our oldest satellite, crosses at around 1:30 or so p.m. So although you can't see them, if you look up in the sky, just know at about 10 o'clock in the morning, you probably have a satellite flying over Medellin here. When your satellite flies over, it has what's called a field of regard. So that's just how, or the area in which it could take a picture itself. So it can only look off to one direction or the other so far, and that's kind of defined in that cone shape right there. And then after that, you have a field of view. So within that round shape that we can possibly look, we actually see how big of a picture that satellite can take itself. So all of our customers are planning around these type of things in order to get the best, highest quality picture that they can. There on the right, you can see what's called an off-nadir angle. So if you look straight down, that term is called nadir. So it's as if you're looking just straight to the ground. An off-nadir would be you looking away from that at a specific degree. And the higher you look away, or the further you look away, the worse the picture looks. So imagine if you had like goggles on and you're looking straight down, you might be able to see a meter diameter beneath you. Well, if you look up at 30 degrees, you could probably see like 3 meters. So we just have that much loss of resolution. And this is a kind of a table that shows how that is. So at 0 degrees, so we're looking straight down, you can see that first satellite. It has what's called a 31 centimeter resolution. What that means is that every single pixel you see is 31 centimeters. So if we took a picture of an empty parking lot and you placed a sheet of paper in there that's roughly 30 pixels long, you would see a black image and then a white dot for one of those pixels representing that sheet of paper, just to give you an idea of the resolution that we can see with the satellite pictures themselves. So as you can see here, when you're looking straight down in that yellow box, that would be a low off-nadir image. So you're looking straight beneath you and you take a picture. If you look off at a higher angle away from that, you get that larger picture itself because of just how the sensor in the camera works and seeing that different field of view. Here's a good example of it too. So on the far left, I think that says 1 meter resolution versus 70 centimeter resolution versus 30 centimeter resolution. So just to give you an idea of the fidelity of different pictures that we take. So then our customers, basically what they see when they want to reserve a satellite from us, there over North America, you can see that outer green ring. That's the communication area of which an antenna can talk to the satellite itself. So I said, as it flies overhead, we point that satellite dish at it. Because of the curvature of the Earth, we have to be about 5 degrees over the horizon. So from 5 degrees to 355 degrees, we can talk to that satellite, which kind of produces that green round signal. And then those yellow lines are the paths that the satellites follow over the world. So they're going from North Pole to South Pole, essentially. Customers get access to every other one. Our primary customer is the US government. So they actually get every other pass to themselves, and then everybody else gets every other one to share. So that's why you see in dark green lines there, the potential contacts that we would have with those satellites. And then the yellow dots would be the different areas that we want to collect an image of. So this is kind of how our customers would choose which satellite access they're interested in. Because remember, they're renting an amount of time. The more images that you can collect in that time, the better your money's well spent. So would we want to rent the left one and only collect 2, or would we want to rent the right one and collect 10? At the start of that time, we call these access windows. We have a brief uplink contact period, which lasts about 7 seconds. That's when the antenna talks to the satellite and says, this is what I want you to do. Then we start our imaging region where we're actually collecting pictures themselves. So that satellite's sitting there moving around, taking pictures. and simultaneously downlinking those pictures back to that customer for viewing themselves. After that, we have to return that satellite to a handoff attitude, it's called. So imagine it's flying this direction, looking straight down. We take control of it. We start taking pictures over here. At the very end, we have to return it to that original position. So that way the next person that uses it knows where it's going to be pointing, so they have a predictable behavior to them. So we have that return to handoff attitude, and then we exit that access window. So this is just kind of a little concept diagram. We call them in the aerospace industry ConOps, so concepts of operations. That just explains how information flows through a process. So here you can see that we have a human operator. They enter an order that they want. It goes to our collection planning system. So that's where they would plan out what images to collect. We would then request time from Maxar to rent that satellite. Once that access window is approved, we would then finish our collection planning. We would then figure out a way to task that satellite. So there's a few ways to do it. We can do it directly from our own satellite, or we can virtually give those plans back to my company, and we'll upload them onto that satellite with one of our own ground terminals themselves. That spacecraft goes and executes that collection, and then similarly, it'll downlink it directly, or it'll virtually downlink it back through Maxar, of which will deliver that information to the customer, and they'll go and produce an image from it. So that's what my company does, and the program that I work for does. Now, what specifically do I do as a systems engineer? I basically define what work is. So I don't actually do work, I just define what work is. So if we went back to that last one, that flow of information, all those different components that talk to each other and how it has to maneuver through that, I would define what that is. So there's this model called the Systems Engineering V. So we start with that concept of operations. We then break that down into what the requirements to make that happen are. And then we go into a detailed system design. Then somebody else actually does that bottom part where it says implementation. I pass that work off to another employee or another group who will do some of the coding and the programming and things like that. They'll give the work back to me, and we'll go through integration, test, and verification. So that's confirming what they did works. And after that, we'll look at it at an overall system level. So we'll take that small piece, put it in the whole system to confirm that the system works as a whole. And once it is, we will go ahead and ship that off. And then we would move into an operation and maintenance phase where, you know, a customer has this DAF system, and we just want to make sure that it's continually working for them. So as a systems engineer, I essentially define what work needs to be done. I don't actually do that work myself. Specifically, I'm in charge of working on this program called SecureWatch. It's very similar to like iTunes, where you'd sort and save music, except for pictures. So it's a visual representation of all the different pictures that a customer has taken. They can browse them in like a catalog and view changes over time. So as you can see here, this is an atoll outside of China. In 2014, this is what that island looked like. There, 2019, 5 years later, you can see how much it's developed with an airstrip on there, the housing, and everything like that. So customers want to track these things over time to see changes in the earth. So just a quick example of my work, kind of like I talked about. We start off with our concept of operations. So in that case, it would be somebody wants to order an image that they've already collected. So we want to reproduce that image itself. So then I would look at the sequence of events that have to happen in order to make that process exist. I would break down the different requirements of what's required in order to make that happen, pass that off to a development team to develop those, and then we would integrate, test, and verify, and then put it in our whole system to verify that that works. And then we would move on to training and operations support. So I do travel around the world a lot to go to various customers to train them on our systems and do the operations support as well. So yeah, that's basically what I do.